Our last topic in this course is going to be about geometry problems. And geometry is a very large area. In fact, it's an area that I do research in. And so we're only going to barely touch on pieces of it here, but there's some general principles that apply to a lot of geometry problems. And these are the sorts of things that you might run into where you're computing distances between points and sort of basic geometric calculations. When you get into 3D geometry and curves and all sorts of things like that, it gets a lot more complicated. But generally, those aren't the problems that people run into in a more common setting. So the key thing to think about when you're dealing with geometry problems that you would typically run into are to build up from simple pieces to more complex ones. And many of the operations that you need to do that are geometric calculations, really, by the time you get to the final calculation, it should be something that's very simple if you have built up all of the infrastructure along the way. And so when you look at the coding example that I'll do in class, the code, I'll show you sort of how you can build up very simple things and put one thing on top of another, and you can get to much more complicated calculations just from a series of much simpler things. So let's talk about some of this. Most of what I'm going to talk about today will be 2D, but a lot of this, not everything, but a lot of this will extend very easily to 3D. So even though many of the examples I give are in 2D, much of it extends to 3D. There's a couple of cases where that's not true, but most of it will. And let's start with the simplest thing that we want to represent. Those are points. And you should all be familiar with how points get represented. You basically have an X value and a Y value. And you can calculate things such as the distance between points. So if I say that I've got a point P, I'll usually write it as Px, Py with subscripts. And if I've got a point Q, I might write it as Qx and Qy. And so if I want the distance between P and Q, then I can write that as the square root of Px minus Qx squared plus Py minus Qy squared. And of course, if this is in 3D, you would also have a z component here, and you'd get Pz minus Qz squared also in there. Okay, but typically you don't need to worry about that part of it. That's for 3D calculations. So you can calculate distance between 2 points. It's pretty straightforward. Kind of the next thing that you might imagine dealing with after points are lines. And believe it or not, lines have a variety of ways that you can represent them. When we say line, we often mean very different things. So one example of a line is the infinite line. It's the line that goes on to infinity in every direction. Another example of what we talk about when we say a line is we want a line segment that has a starting point and an ending point. Sometimes we want to be able to switch between those two representations and so on. Now, one of the ways that we can represent lines is in an implicit form. And this is the way that you might have learned about a line back in elementary school. This is where we represent a line as ax plus by plus c equals 0. And if you sort of manipulate this around in various ways, you can easily imagine converting that into something where you get y equals mx plus b. Notice that b in this case is going to be minus c divided by b, and your m here is going to be minus a divided by b. And this works well. However, it obviously does not work well if b is 0. In other words, if you have a line that cannot be represented in this form. Okay, so for instance, what if you have the line x equals 3? Well, guess what? You can't write it like that. Okay, so a line that does not include y in the implicit form, you can't represent that way. So this is actually the more general form, even though there's kind of an extra degree of freedom. Notice you have 3 coefficients, a, b, and c, but a line, you only really need 2 things to represent it. That's normally you would use your slope-intercept or something like that to represent it. But that's the form. Now, sometimes the implicit form of a line is the most useful form, but it's not typically the one that you use in geometric problems. The cases where you want to use it, it's super useful, but it's not the most commonly used. A more common way of representing a line is as a pair of points. And so we actually represent the line by 2 points, and I'll call them P and Q, or maybe just P1 and P2. So P1 and P2, and those are a point 1 and a point 2. And this can represent the infinite line that passes through those 2 points, or it can represent just the portion of the line starting at one and ending at the other, so just the line segment. Okay, so the pair of point methods, or the pair of points method, can be used for either one of those. And very closely related to this is the point vector method. So the point vector method says I've got a point and I've got a direction for that point. And so you need to have some point P and you have some vector V that is represented that way. And now for either of these, whether it's the pair of points or the point vector, we can generate more points on the line. That's one of the things that's very nice, that's difficult to do with the implicit form, is we can easily generate a new point on the line. For instance, if I take the point halfway between P1 and P2, guess what? That's on the line here. If I want something that's P plus 2 times V, well, that's another point that's on that same infinite line. The other thing about these two representations is they can give a bound. They can actually represent a line segment. So it's kind of obvious here in the pair of points representation. In the point vector representation, you'll often assume that V is of length equal to whatever the length of the line segment is. So it gives you V gives you the direction and the distance for that particular line. Okay, so point vector, you'll sometimes see this called point ray because the vector has a starting point and it has a direction that's used along the way. Now, when you have this point vector representation, well, first of all, you can get this. You can always transform pair of points into a point vector representation by just setting V equal to P2 minus P1. So that's a very simple approach. And likewise, you can go the other way by just saying P2 equals P1 plus V. Okay, so you can always convert between those very simply. Okay, when you have this point vector representation, this is a way of doing a parametric version of the line. And we'll often use a variable S to describe how we move along a line. And the idea is we can define any point as P plus V times S. And so if S is 0, so when S is equal to 0, we are at the point P. And when S is equal to 1, we are V away from P. And notice that if S is a value greater than 1, it means we go farther in that direction. If S is a value less than 0, it's at some point along the line before that. And so when S in this formulation is in the range 0 to 1, we are on the line segment. And when it's less than 0 or greater than 1, then it's outside. And that's a very useful representation for lines. Now, when we have lines that are represented like this lets us do a few operations much more easily. So one of those things that we can do is we can intersect lines. Okay, and so the idea of intersecting lines or intersecting line segments is if I think of infinite lines in 2D, so this is where I have something in 2D, and it matters that it's in 2D, because two lines in 3D space, those lines don't generally intersect. You can maybe calculate the distance between them, but they don't intersect each other. Okay, so if we want to intersect lines in 2D, there's actually a few different methods for doing it, but one way of doing it is I take one line, so I have P1, and I've got this vector V1, and I've got some other line P2 with some vector V2. And so those are my two line definitions. And what I want to do is I want to find what's the parameter S along this direction and what's the parameter T along that direction. And this point where they meet is going to have some particular ST value where they meet. So in other words, we are wanting to solve P1 plus S times V1 is equal to P2 plus T times v2. And these are vectors, and the points are kind of a vector quantity also. They have both x and y components. Okay, and so this has to be true in both x and y. And so the way we can write that is p1x plus s times v1x equals p2x plus t times v2x. And likewise for y, p1y plus s times v1y equals p2y plus t times v2y. Okay, and now notice that we have two unknowns. We have s and we have t. Those are my two unknowns, and I've got two equations. Two equations, two unknowns, we can solve for that. There's different ways you can think of doing it, but the basic idea here is that we can use that to calculate s, and we can calculate t. And if I wanted to actually write all of this out, I'll write it out just so that you can see it here. The basic idea is you would solve for one of these and plug it into the other one, and you can get results like that. But down here in the bottom, let me show you the form of this: v1x, v2y, v1y, v2x is going to be in the denominator. That's going to be true of both of these. Okay, and the numerators are going to be more complicated. This will be something like p1y v2x plus p2x v2y minus p1x v2y minus p2y v2x. And this one will be p1y v1x plus p2x v1y minus p1x v1y minus p2y v1x. Okay, so those look complicated, but notice that if you were to actually code this up, this is actually a pretty simple thing to code up. It's just multiplying a few numbers together and adding them. So if I'm given these values, if I'm given p1 and v1, this is a really simple computation. It's nothing complicated. Now, one thing to be careful of is looking at the denominator down here. Is that denominator, it's common, and if it is 0, what that means is that the lines are parallel. Okay, it means that you've got two parallel lines, and therefore they're basically the point at which they intersect is at infinity. The s and t values are infinitely far away. So you always want to put some sort of check in there and make sure that you don't have a parallel line. Anytime you're doing a line intersection test, make sure you check that denominator, make sure you know that those lines are not parallel to each other if you're going to try to get the point. But once you do, now you have the s value and you have the t value. And so you can find, if you want to get the coordinates of that intersection point, you just plug in s and t into these equations, and you should get the exact same result. If you plug s in here, p1 plus s times v1, you should get the same thing that you get if you were to plug in p2, if you were to plug in for t here in the second one, and p2 plus t times v2. So those should come out identical to each other. Okay, so that's an example of intersecting two lines. Now, if you want to, that's going to give you the intersection of the infinite lines relative to each other. If you actually want to see, are the two line segments intersecting? So for instance, these, notice that those lines, the lines might intersect, but the line segments don't. Or you might have something where a line intersects one of them, but not the other one. Well, for these to both intersect, think back to the definition, and you would see that both s and t must be in the 0, 1 range if the segments intersect. Okay, so we have to have them both in that range if we're going to have intersecting line segments as opposed to the infinite line. Okay, so that's an example of what you can do there. There are There are other things you can do. You can get the distance between a point and a line. And before I show you the distance between a point and a line, let me describe a couple of things. First of all, notice, so I've talked about points and I talked a little bit about vectors. Remember, I have the vector v. Remember that you can get a vector is 0.2 minus 0.1. And this is a vector from P1 to P2. Okay, so the vector from P1 to P2 is the 0.2 minus the 0.1. That's going to give you the vector from one to the other. And there's things that you can do with the vector. You can use it, you can get the magnitude, okay, which we often write like that. So the magnitude of V, and the magnitude of the vector is the square root of Vx squared plus Vy squared. So plus, okay, so Vx squared plus Vy squared. We can normalize it. So often we write a vector with a little arrow over the top. We can write a normalized vector. We can make it unit length by taking our vector V and dividing it by the magnitude of V. Okay, by dividing it by this value, and that's going to give us a unit vector. And hopefully all of this is something that you remember from back in physics, if not calculus or something like that along the way. But it's the sort of thing that you should be used to thinking about when you think of directions and all of that sort of stuff. So it's a pretty basic geometry that you have there. Well, once you have vectors, there's some really interesting things that you can do with them. So if I'm given two vectors, and this is the sort of calculation that you do all the time in computer graphics, by the way. If I'm given two vectors, I often want to know something about this angle between them, theta. And so if one of them is vector v1 and the other is vector v2, I can calculate theta from the property that the cosine of theta times the magnitude of v1 times the magnitude of v2 is going to be v1 dot v2. And if you don't remember what the dot product is, the dot product is, remember, we have our vector v1 is going to have an vx and vy. So this has an x value and it has a y value. I'm sorry, I'm not doing this very well. It has a value v1x and v1y. And vector v2 is going to have values v2x and v2y. And the dot product v1 dot v2 is v1x times v2x plus v1y times v2y. That's the definition of the dot product. And if it were in 3D, you'd also add on v1z times v2z. Okay, so what this means is we can calculate, if I'm given two vectors, I can calculate the dot product. That's actually a very simple calculation. Again, if you write the dot product, you can write this in one line of code. If you write a function, you have the header line and then one line in the body, to calculate what the dot product of two vectors is. Okay, and so if I want to find the angle between them, all I need to do is calculate v1 dot v2. I might need to divide through by the magnitudes of each one, although I'll talk about another thing in a second. And then I take the arc cosine, and that's going to give me theta. Okay, now notice that if I divide these magnitudes over here, divide v1 by its magnitude and v2 by its magnitude, those are the normalized unit vectors. So another way that we can write this is cosine of theta is going to be v1 hat dot v2 hat, the dot product of the normalized vectors. And then I don't have to worry about the magnitude of each one. And so if I want to get theta, I just take the arc cosine of v1 dot v2. Okay, so that will tell me what the angle between them is. Now, one thing that it does not do, just to be clear about this, is it's not telling you the sort of direction of the angle or anything like that. This is going to give you a value from basically 0 to 180 degrees. And so it doesn't matter if this is V1 it doesn't matter if V2 is over here at an angle theta or if V2 is over here at an angle theta. Those are both giving you, all you're going to get out of the cosine function is theta. And the reason for that is, if you remember your graph of the cosine function, it's symmetric around 0, so it can't really distinguish whether you're on the positive or negative side. Now, one of the things that can distinguish that is the cross product. So the cross product, you might remember your right-handed rule. Whenever you learned about this to begin with, the right-handed rule says I take a vector in one direction, I point my fingers in that direction, and then I curl my fingers toward the next vector. So let's say this is the next vector. I'm going to curl my fingers that way and stick out my thumb. And what direction is my right hand? What direction is my thumb pointing? Well, in this case, it's pointing out of the page. It's coming out of the page. If instead I went and I pointed my fingers in that, and then I curled them in that direction toward a vector going in that way, I'm going to be looking into the page. It's going to be, my thumb will point into the page in that case. Okay, that's your right-handed rule. And so the thing is, this value here, this is going to be positive cross product. And this one over here is going to be a negative cross product in 2D. Now in 3D, this just tells you the direction. You're getting a 3D vector. And basically, this is going to say, I'm getting a vector that's either coming straight out of the page, or I'm getting one that's pointing straight into the page. And so that's what the positive and negative mean, is out or in from the page. So now the cross product, which I can write as V1 cross V2, I can actually define what that is. And I'll admit I can never remember the cross product formula. I always have to remind myself of what it is, but it is V1x, V2y minus V1y, V2x. Okay, that is the definition of the cross product. And if that thing is positive, that means that my vector V1 and V2, if it's positive, and over here I've got V1 and V2, positive, it means that the new vector that I have is in some left-hand turn from where I am. And if it's negative, it means it's some direction that goes around to the right, all the way back to 180 degrees. So if I'm going straight forward, if they're identical in the same direction, it's 0, or if they're exactly opposite, then this comes out to be 0. But otherwise, that's going to tell me whether something is positive or negative. And this is a key thing when we talk about in the last lecture that we have, I'll be talking about a convex hull algorithm. And this is one of the key parts of the convex hull algorithm, is whether this number is positive or negative. If it's positive, I'm making a left-hand turn. So left turn is positive, and a right turn means negative. So those are equivalent ideas to each other. And if it's 0, it means they're either both in the same direction or both in opposite directions. So the cross product is going to be very useful to tell me, am I turning left or am I turning right? Now, if you say, well, okay, I need to figure out not just what this is, I need to know some more stuff about it. Another thing that you can remember is that the cross product is defined, the magnitude of the cross product of V1 cross V2. So the size of that is equal to the size of V1 times the size of V2 times the sine of theta between them. Okay, and so if these were both unit vectors, then this and this become 1, and so it's just the sine of theta. Okay, the other thing is, if I take two vectors and I take the cross product, what I get is the area of that parallelogram. And so if I think of half of that parallelogram, I can think of that as a triangle. And so if I imagine that I've got vertices A, B, and C, okay, I can form the vector AC and the vector AB, and I can take the cross product of each of those. If one is V1 and the other one is V2, if I take the cross product, then the area of the triangle ABC is half of the cross product. So the area of a triangle is 1/2 the cross product of the vectors of two sides. So given any two sides, I can calculate the area of that just by taking half of the cross product, and that's the definition. Okay, let me go slightly on a tangent just for a second. The cosine I mentioned before, the cosine, if this is where I am, it can't tell me whether I'm going to the left or to the right. The sine function can. It can tell me whether I'm going to the left or to the right. The problem is the sine function can't sort of resolve those two things from the ones going forward, whereas the cosine sort of can, or you can think of that. It's basically at what point it's symmetric. So if you want to actually figure out what angle one thing is relative to another in terms of 3D, or not 3D, in terms of 360 degrees. So you want to know, is it going all the way around like that as opposed to just a certain amount? You need to use both the sine and the cosine. And the way that you can do that you can incorporate both of those is if you use the tangent function. And so there's often a built-in function in C++. It's the form is atan2, and atan2, what you need to do is you need to actually have a numerator and you have a denominator, and you pass the numerator and denominator in separately. And if you remember the way that the tangent is defined, another way that you can define it is as sine over cosine. Okay, so it's very common to find the sine and the cosine, and if you were to find those, you can put that into the atan2 function. But basically, if you're needing the full 360 degrees, atan2 is your friend. You can always get the angle from that. Okay, so let's see. Let's review some of the stuff that we've just gone over, because that was kind of quick. We've talked about vectors. We talked about the dot product and how the dot product can find the angle between two vectors. We talked about the cross product. We talked about how the cross product can tell us whether we're turning left or turning right as we go from one vector to the next. And let me just point out one more thing on that. If I'm going here and I'm going there, that's the same. Remember, they're vectors. That's the same as if I put that thing back there. So either way, those are sort of the same calculation, going from one to the other or the other way around. It's all the same. So it doesn't matter, for instance, if I've got points if I've got point A, B, C, it doesn't really matter whether, if I'm just trying to determine, do I go left or right? It doesn't matter so much, am I going to go A, B, and B, C, or am I going to look from A, B to A, C? Either way, it's like going left or going right. The question is the same, regardless of which of those two pairs of vectors you form, whether it's the two that are in black here or the two that are in blue. Okay, so we went over the cross product. We also talked about how you can use the cross product to find the area of a triangle. Just by forming two of the edges as vectors, you get the area of the triangle from that. Okay, let me now that we've talked about vectors a little bit, let's go back briefly to lines. There is a way to find the distance, if I want to find the distance of a point to a line. What I can do is I can form the vector here. So this is going to be P1, and I'll say this is P2, so that this is my vector V. Okay, I'm going to form the unit vector V hat. Okay, so in that direction V, I'll form the unit vector V hat. I'll form some other vector here, W, that is the point that I want to know. And one of the things that I can get from the dot product is I can get the projection of a point in some direction. Okay, so if I take W dot V hat, this dot product is going to project W in the V hat direction. Okay, so let's call that an amount U. Okay, let's just call that that number U. What that's going to do is that's going to tell me that amount U. It's going to tell me what that distance there is. Okay, and so the nearest point on the line is P1 plus U times V hat. Okay, this is going to be the nearest point to point P up here. The nearest point to P on this line is going to be right there, and that's the point P1 plus U times V hat. Okay, and so I can take the distance now, the distance between point P and P1 plus U times V hat, that's going to be the distance here from the point to the line. Now, one thing I will point out is this is the infinite line. It's the line, it's going to give you a point somewhere on this line, depending on what U is. If U is less than 0, then it means that point P is located over here, and it's going to give you this value. It's going to give you a point on the line somewhere over there. If U is bigger than the distance from P1 to P2, so if it's bigger than this entire distance, it means it's going to be somewhere over here. And so if what you actually want is the distance from a point to a line segment, then you need to calculate and say, what is U? Where does U fall? If U falls back here in that region, then you want to compare versus the first point. If U falls in this region, then you want to compare to point P2. And if it's somewhere here in the middle, then you use this value here. Okay, then you're going to compare to that point that's the nearest point on the line. So when I'm comparing a point to a line segment, what I do is I calculate U, just like we said here. Okay, and again, what we do is we form a vector from the starting point to P. That's our vector W. We form the unit vector from P1 to P2, so it's that vector V. We turn that into a unit vector. And then we take the dot product of those two things, and that's going to give us U. And once we have U, we figure out, is it before P1? Is it after P2? Or is it somewhere in between? And then, depending on that, we are either going to calculate the distance to P1 if it came before. We're going to calculate the distance to P2 if it came after P2, or we're going to calculate the distance to that new point on the line if it fell in between. Okay, so that's how we calculate the distance from a point to a line. We need to have kind of all of the infrastructure built up. Okay, so notice, if I were to tell you, tell me the distance of a point to a line segment, that sounds like a complicated process. But if you have all of the infrastructure in place, if you've already defined my dot product, and I've already defined how do I get a unit vector, and I know how do I calculate a vector W as the difference between 2 points. If I've already defined all of those things, then this becomes an easy operation. It's just a pretty simple thing to calculate this and plug in the values and then calculate distance between them. But you had to build everything up to that point to begin with. Okay. I think the last thing that I really want to talk about, excuse me. Last thing that I really want to talk about is about a point inside of a polygon. And I'll just mention, maybe I'll mention one other thing first. Let me just mention area for just a minute. Excuse me. Often we will end up with a polygon that is not just a triangle or something like that. We talked earlier about how you can find the area of a triangle using the cross product function. Well, if I'm given a polygon, I can divide a polygon into triangles like that. Okay, so there's 3 triangles that you have along the way. And you can pretty much start at one vertex and just march around and take pairs of 3 vertices and sum up the areas of all of those. And this even works if you have a polygon where some of the stuff is negative. Okay, so in this case, I might form it starting here. I might go from here to here to here, and I get that blue triangle. And then I go from here, from there to there to there, and I get that green triangle. And this one would have a negative area the reason it would have a negative area is the cross product would be negative. I would be going from here to here to here instead of the other way around. It's a right-handed turn. I would get a negative area triangle. And so it would basically subtract off that entire green area. Then when I take the next one, I would take that and notice that's going to add back in. It's going to add back in some of that area. And then the final one that I have is that magenta one. And notice that the magenta one, now if I add up the blue and the yellow and the magenta and I take away the green, it all adds up correctly and I would get the area of that entire polygon. Okay, so area of a polygon you can get just by adding up the stuff along the way. So there is another calculation that it turns out, again, once you have built up all of the pieces, it turns out to not be so bad, is you can check whether a point is inside a polygon or not. Okay, and so one way of doing that, and there's probably 4 or 5 different ways I know of for calculating whether a point is inside a polygon in 2D. But one of the ways you can do that is you can order all of your points in a counterclockwise order. Okay, so like 0, 1, 2, 3, 4, like this. Okay, and what you do, and what you can say is if this is a convex polygon, in other words, if it doesn't have any like pieces that cut into it like that, okay, that is concave, that's a concavity, so that is not convex. But assuming you have a convex polygon, well then any point that's on the inside is always a left-hand turn away from any edge. So 0 to 1 and then 1 to that point has to be a left-hand turn. 1 to 2 and 2 to that point is a left-hand turn. 2 to 3 and 3 to that point, a left-hand turn. 3 to 4, 4 to that point. 4 to 0, again, left-hand turn. Everything would be a left-hand turn if it's a convex object. If it's not convex, if you have something and so you can check and just say, hey, is it always the left-hand turn to go to the inside? If so, I'm inside of the polygon. And so notice a triangle is always convex. You can't have a non-convex triangle. Once you get a quadrilateral, you can have some quadrilateral that's not convex like that. If you have a non-convex one, there's other ways you can do that as well. And you can actually add up the angles from the point inside to each of the vertices along the way. So if I've got some potential shape like this and I've got a point inside, I can basically form vectors and I can add up all of my angles to everything along the way. And if I'm inside these angles, if I do them and I subtract off some angles and add on other ones, if they add up to 360 degrees, then I'm going to be inside. And if I'm outside, they are not going to add up to 360 degrees. In fact, generally, they're going to add up to 0. So either all of those angles are going to add up to 360 or they're going to add up to 0. And if you have a very simple shape, like imagine this one and imagine this point, it's very easy to see that if I take each of those angles and add them up, they add up to 360. And if I have the same thing, but I'm outside, well, I get some angle there. And so those are the 4 that I have. I'm going to have a positive angle for this one. I'm going to have a positive angle for that. I'm going to have a positive angle for that. And then this angle down here is going to basically be negative, and it's going to add up. It's going to subtract off everything that was there along the way, and I end up with a 0 value for that point that was outside. Okay, so the idea here is it's relatively easy to do a point inside a polygon test if you already have some of the other infrastructure in place. If you already have your check to see, are you making a left-hand turn or not? If you already have something that lets you know the exact angle, including positive and negative angles, you can use either of those things, and then the point inside a polygon check becomes okay. So the theme of all of this, again, is build up a basic library of functionality. As you're doing these operations, you should almost never have something more than 10 or 15 lines, and often it's just 1 or 2 or 3 lines of code to do any one thing. And if you've built everything up correctly, you're just calling simpler functions. You know, you are using a difference operator, you're doing the normalization, you're doing a dot product, you're doing all of that, and you're not trying to put it all into one routine that does all of it. You're just calling these things that you've defined otherwise, and then it becomes a lot easier. So the last thing that I want to mention is something that comes up. It's a practical issue when you're doing geometric calculations, and that is there is floating point error. And there are what are called degeneracies. And so degeneracies are things where, you know, for instance, parallel lines. It's things that wouldn't happen in general, but you can have special situations where they happen. If I just gave you 2 random lines, they're going to intersect, but there is the chance in reality that those could be parallel to each other. And so these are things that you always have to check for. So this is basically checking for 0 or for special cases. And in a lot of geometric problems, you really have to pay attention to that. You have to make sure, if I want to calculate, oh, I have a point and a line, what's the distance? I need to make sure I check to see, is the point already on the line? If I want to determine, am I making a left-hand turn or a right-hand turn, I need to make sure I handle the case where I've got 2 things that are right in a row. Now, sometimes you'll have a problem and they say, we guarantee stuff is not in a row. In real world situations, you can't have those guarantees, and you need to make sure that you handle all of this stuff along the way. We talked before about having parallel lines, all of that sort of thing. And all of this gets magnified by problems of floating point error. When you do floating point calculations, you're all familiar with the little bits of round off error that you get. Well, these things can kind of compound. And the reason that that's a problem in geometric calculations is you might have one thing and you might have another vector, and you want to know, am I making a left-hand turn or a right-hand turn? And the little bit of numerical error that doesn't seem like it should be so bad might change that point from being a left-hand turn to a right-hand turn. So even though there's only a very small amount of error, you're making a decision. Did I turn left or did I turn right? And that can change everything about what you decide. So it can actually give you the completely wrong answer if you make the wrong choice of whether something is left or right. And it can all be due to the floating point numerical round-off error and the way it builds up over time. So I just say that as a caution. When you're doing geometric calculations, you've got to be especially worried about floating point error, making sure that you're not relying too much on stuff that's really close to 0. And you need to make sure that you account for degenerate situations, things where where 2 things exactly overlap or exactly line up, even though that wouldn't seem like a general situation. But other than that, just build up your functionality, and you can end up performing fairly complicated geometric calculations where any one piece of code is actually pretty small, assuming you've sort of built everything up from there.